Throughout pop culture, the concept of a mothership or extraterrestrial spacecraft has been a recurring theme within science fiction. What if we could actually detect these types of spacecrafts using modern technology and physics? Gianni Martire, tech entrepreneur and co-founder at Applied Physics, along with a highly esteemed think tank, proposes a method for detecting extraterrestrial spacecrafts using gravitational waves. Join us as we get rebelliously curious. Gianni, thank you for joining me on Rebelliously Curious today. So you are the co-founder of a company called Applied Physics, and you have recently released a paper that discusses how you'll potentially use gravitational waves to detect alien spaceships. So before we get into the nitty-gritties about the paper, can you tell me a little bit about Applied Physics?
Yes, of course. Well, first, thank you so much for your time. I really appreciate you having me on your show. So Applied Physics is similar to like a Bell Labs. Like, I don't know if you're familiar with the Bell Labs from the 1990s, but it's a think tank. So it's a physics think tank. And we basically, we have IP, we have patents, commercially viable ones, and then, and more moonshot patents, like stuff we do in warp. But this stuff, obviously, it encourages people to join Applied Physics because we're always at the cutting edge of science. So Applied Physics is a physics think tank. We survive in our own IP. And this is our own research that we do. This is kind of like our X Labs. And it's just fun science for us to do. And it also allows us to really hire high caliber scientists because, who doesn't want to work in this type of stuff? So it allows us to be more inventive with our practical solutions for commercial applications that tend to be more boring than warp drives. But, when you have a creative group of people in the room, you kind of come with the solutions much quicker. So that's how the model works. And that's what Applied Physics is.
Start off first so people that if they don't know, what are gravitational waves, and then how are you using them to identify potential ET spacecrafts?
Yes, so basically a gravitational wave is anytime you have a distortion in space-time per general relativity, you have a ripple, as Einstein talked about it. And that's why we go around orbiting bodies and so forth. So these little ripples, anytime you have any mass that moves at any given speed, so like it has to move at a meaningful speed and it has to be a meaningful mass, it will create meaningful gravitational waves that we can see. So gravitational distortions. So the same way that an analogy would be the same way let's say you're in a lake and you're looking at the water and a jet ski passes you. That distortion of the water is no different than the gravitational distortion of, like, say, like a small comet passing you. Now, like, say, a big boat passes you. You're going to see a distortion field in the water. Now, that distortion field is going to be much more significant, but it's going to be very similar. But that's a big, massive planet. So that's the same thing. Analogy is one-to-one. So what do these scientists do with all this fancy math? We're basically looking at the ripples. That's it. Like, to make it very simple for everybody, we're looking at the ripples. And it's like, well, how do you know you're not looking at a jet ski or a boat? Same way you look at the ripples. Like, can't you tell? Well, how do you know you're looking at a planet? How do you know you're not looking at a star or a rogue planet, of course, because of how it moves? That's, obviously if it's going around the planet, around the star, we know it's a planet. And how do you know it's a warp drive or a ship? It's like, well, look in the direction it moved. When does nature ever do that? So that's basically what gravitational waves are and what we're doing and how to measure them. And really how simple it is. We're just looking for anything that looks out of the ordinary outside of nature. But at the same time, our project, we had to increase the visibility of LIGO and really clean up the data and come up with machine learning technology to do that. So because again, we're monitoring the universe through gravity waves. So we're not just monitoring for warp drives, that's the fun thing, but the real practical science, it picks up anything. So like it allows us to monitor universes away. So it's not just about learning about our galaxy. I'm like, no, there's thousands of galaxies. There's an uncountable amount of stars out there. And we really can't measure that with light. That's impossible. We just don't live long enough. But with gravitational waves, we can. We can get a sense of the being of the universe. And the interworking, like a clock, how it moves and so forth. And because we don't really understand it so well yet, there's still a bunch of questions we have in physics. So hopefully this allows us to move the needle forward. And of course, and if we find aliens, even better. It's the field is being increased, seriously without that. But of course, that's the cool thing, and that's the thing we all at applied physics are looking for, because it's great to now that we see the rock in higher definition and higher resolution, that's great. But I was looking for more exciting things, of course.
Because picking something like gravitational waves and looking to detect alien, ET spacecrafts, like it's a pretty big job on its own. So what drew you to gravitational waves to look for these types of objects?
Oh, yes, actually. So the story, how this all happened. It's actually quite funny. So how this all happened. So give you a quick background. So we had published our work paper. This is last year in 2021. And Dr. Alexei Barbarek and I, we presented Introducing Physical Warp Drives, which basically shows that you can actually build a warp drive without negative energy. So it's physical, it's not pseudoscience. So it doesn't require exotic fuels. We could do this with common science today. It's just really hard, but we could do it. It's just very difficult. So because of that paper, it had then attracted a team from Carnegie Mellon and had done some research at CERN. That's Michael Andrews and Manfred Pernini, and Dean of Physics, and they contacted us and said, like, hey, we love your paper, and goes like, why can't we, they were doing some type of LIGO analysis at CERN, and they're like, well, why can't we use LIGO's data to look for your warp drive? Because right now we have what's known as the Barbarek-Martire metric, which is the physical metric that Alexei and I put together. So it's like, well, let's search for it. Is anybody else using that metric? And because it shouldn't be found in nature. So if you find it, it's positive confirmation that, hey, look, somebody else had the same idea and did it and executed on it. And that would be our carrot for humanity. Like, see, we can do it. Now here's an evidence proof. It's so that's how it really started. It was another team that contacted us that was more well versed in LIGO's data because we had thought about the idea, but we didn't think the LIGO would be sensitive enough. Because again, what people have to understand is LIGO was not built to do this. LIGO was built to measure gravitational waves, which it did successfully in 2015, and it became more big announced in 2016, which again, it was almost 100 years to the day when Einstein had predicted them, which I thought was kind of beautiful. So again, it achieved this job, and now it's like, well, what else can we use it for? It's like how people are trying to find more use cases for the Large Hadron Collider, because again, like we spent a lot of money to build it, and it's like, I don't want to destroy it. It's beautiful. But like, to do the same experiment over and over again is kind of redundant and kind of silly. It's kind of expensive and waste of resources. What else can we do with it? So we were thinking about it, like, well, is LIGO sensitive enough to turn it into like a SETI? And when you think about it, like, SETIs, again, I love SETI since a little kid. I've always dreamed of them finding something, but it's like, it's so hard to search with radio waves and it takes so much money and so much time. Again, it's just physics. It's a question of physics. But like with gravity, every day of LIGO's data that I look at, like we look at every day here at Applied Physics, we capture dozens of galaxies around us. So it's right now it's not about can we find signal. It's like, well, can we clean up signal and bring it to the scientific community and confirm it. So like it's the reach of it is impeccable. It's not just a needle in a haystack, because that's really how it's currently working. You can scan the whole universe in one shot. So it's a whole new way of doing astronomy. It's quite beautiful.
There's something called, like you say, it's called a warp signature. So what is the difference between a warp signature and then a techno signature? Are they the same thing or are they different?
No, a techno signature is just like, I'll give you an example. So a warp drive, okay, perfect example. So like a cruise ship, like say aliens do cruise ships too one day, because they have nice moons and they have like these big craft that kind of just go around in a circle. It's for leisure, right? That's not a warp drive, but it's quite impressive. It's a techno. It's great. We would still be able on LIGO to detect that. So that's a different type of signature. So it wouldn't be a warp drive. It's like, well, that's not moving like the Star Trek. It's not the Enterprise. It's more like the Carnival cruise liner, but for aliens. But so that would be a techno signature. So, it's not a warp drive. But it's still very impressive. A warp drive would be then a craft that's moving, that's basically using gravity to distort itself. So, and then the difference, to tell the difference would be, well, listen, everything distorts gravity, as I said before, like a rock. If you throw a rock fast enough, it distorts gravity, especially like at 94, 95% speed of light, you start seeing the curve there. So it's like, well, how do you know you're not just looking at a rock that's just going really fast versus a warp drive? Simple. Oh, the Enterprise is so beautiful that if you can't distinguish it's like when the Enterprise passes you in the lake versus a rock passes, skips you in the lake, bro, you're blind. You're not looking at the mathematics right. Like, look at that pattern, its signature. So that's what I'm talking about, signature. Because like I said, like a jet ski and a boat, they both distort gravity. I mean, they both distort in the water. It all looks similar, and it's all like distortion of waves. But a jet ski will have a jet ski signature to it. A boat will have a boat signature to it. They have a unique pattern. An asteroid will have an asteroid signature to it. So we're looking for a warp signature because, of course, the discovery of another asteroid isn't quite impressive, but we want to find something a little bit more impressive, really just to push the stems.
100%. And so you've written this paper now that you've released. Is there any criticism that you've had from other scientists or other people or physicists or anyone else working? No? Okay, it's amazing.
Yeah, so
That's
actually,
amazing.
so the funny thing is the only criticism when it was actually with New Scientist, it was because they were one of the earliest publications that spoke about it. And I remember I was speaking to Leah, and she goes like, Johnny, we all read your paper in New Scientist. We love it. It's very easy to understand. And she joked that like how it's much easier to understand than the last paper because our last paper was much more complicated. Warp drives is really hard to explain to such a hard topic. But this is more like the signature, and they got it. They understood it. They just go like, but why haven't we done this sooner? Like the technology for this was available. Like we could have done this years ago and started this years ago. And the answer is yes. It just didn't occur to us. Because again, like when you think about it, like, nobody ever thought to use LIGO for a SETI purpose. But when you think about it, it's, oh my God, LIGO and SETI should be best friends. You guys should be talking. It's such relevant to what you guys can do. And the thing is, you can team up because, with every wave in electromagnetic spectrum, you can defer something scientifically about an object that you're trying to measure. So by using a combination of radio, that we're using gravitational to kind of like, where should I point the radio? Because right now we're kind of going like, it's a needle in a haystack, which is really annoying. It's like, well, now with gravitation, like, hey, there's this gravitational anomaly here. That's kind of weird outside of nature. What's the radio signature on it? Let's focus in. Let's all work together and see what it is. And the great thing is, it's like, hey, even if you don't find aliens, you're now still discovering new things about the universe that we didn't know before. So again, even though, yes, we're hopeful we find ET, but at the same time, we're serious, cosmologists and astrologers. Like we're looking for, we're looking to have just better tools in general for the community because that's just needed. But at the same time, if we find something great, well, yeah, that's all the better.
Well, yeah, we've had like Avi Loeb, for example, who has found like something that he's called a Oumuamua. So Oumuamua that has passed by, has gone into our solar system and was detected. And he calls it something of an alien artifact, which we actually don't know what it is, right? But is that something that you would look to work with, like, say, Avi Loeb and the Galileo project? Yes. Would that be something? Okay, yeah. Is it? Yeah, because they're massive craft, or allegedly a craft, right? We don't know exactly what it is. But
I think we determined now that with a Oumuamua, it's more likely just to be a rock, just like a very unique type. Again, it's again in the universe. Again, we're learning ourselves. But no, it's exactly what we need. We need a serious scientist to look at the data, and as many scientists to look at the data. Because here's the thing: there's no shortage of data that we're looking at. We're talking about terabytes upon terabytes. If Amazon wasn't gracious enough to giving us hundreds of thousands of dollars worth of credits, we wouldn't be able to afford to do this type of research. So shout out to AWS for funding this endeavor. But we now it's about analyzing, because like I said, like LIGO was not really built to do this. So is LIGO sensitive enough to detect this at a high scientific standard level? It's not just noise. Can you tell it's not just noise in a warp drive? So we need people like Avi and more scientists in the field to really help us analyze the data. Because again, there's just now a wealth of data. So the good news for all the enthusiasts, it's not like, oh, we don't have enough information. No. We have a lot of information now. We just need a party going on, and really people just dissect information. And that's why at Applied Physics, we're more focused on making the tools for people that you need to really clean up the noise for this data. Because again, the tools, because it's not the most popular type of research right now, the tools available that are off the shelf just aren't the most sophisticated, and they're very expensive to run. So we had to come up with more efficient ways to do this type of research.
That's amazing. And so now what is next for applied science? Where are you guys looking outside of
Applied physics.
gravitational waves? Yeah, what are you looking now? What are you looking to do with the company and where are you going next?
Well, yeah, we're just going to be launching our patent portfolios. Right now, we've kept it pretty quiet. We're just talking about gravitational waves and the fun physics. But we have more practical stuff, the commercially viable stuff that, for today's consumer products. We have that coming out more next year. But we have a lot more fun stuff in these sciences. Because again, we want to show people how beautiful the science is first. And then to show people the other applications of it. We want to get the party started. So right now, it's we're going to be focusing more on warp field mechanics and all this other stuff, and then the practicality. Because funny enough, and we were chasing passion. Again, we're all just physicists that obviously our inner childs are alive and well, and we realize, and this happens at Bell Labs all the time, and all these in the Palo Alto Research Center. It's when you have the scientists and we have this rule of applied physics, and we let people chase something every now and then. It's like just let them chase their passion because they'll find something practical and applications like, hey, this was useful for this reason. And now look, we found a commercial application for it to pay for the research. But again, everything has to be symbiotic. So it's like we only want the research to continue. So we have to find ways to monetize it for profit, of course. But again, when you're doing practical things and valuable things, that's easy to do because you're not just doing something for the sake of doing it.
Can you explain to me what a ramcraft is? Because this is broken down in your
Yes.
paper, but can you break it down for us so that somebody understands what that terminology is and what it stands for in your
Yes.
terms?
So thank you so much for that question. So Ramacraft is actually a term of a tribute to the Arthur C. Clarke book, Rendezvous Rama, which I'm sure a lot of us read when we were kids. And that's that big spaceship that just shows up one day. And, it's like it shows up on our radar. And we're thinking like, well, what should we call this radar system that we made? And we were thinking of Rama, and then we realized like, oh wow, it actually works because rapid and or massive is what we use Rama, the abbreviation. Because what is this? What does this look for? As you were asking before, does it look for technical signatures or warp signatures? Well, it looks for both, and that's why we call it a rapid and or massive accelerating object, so like a craft. So that's a Rama craft, and then we call this the Ramadar because what is the apparatus because for detecting and ranging. So it's that's what the Rama acronym stands for. So it's a tribute to Arthur C. Clarke, and also a good way to remember that we're looking for rapid and or massive objects moving in ways and patterns that are just outside of nature. But even inside of nature is still interesting. But of course, we want to look for something new.
Is there anything else that you want to add that I might have missed?
It's easy to tell the difference between a jet ski and a boat when you're 2 feet away from in the same pond. But now imagine that pond is like 100 light years away, and you're trying to tell the difference between a jet ski and a boat. Now, you see, that's why you need all this machine learning software and that whole to do this. So like that's like the next step. So like if you want me to mention that, but like I think that's going too much into the weeds. But it does like in terms of like the difficulty, like well, why is it taking for you guys to figure out if you have a warp signature or not? Like it's really far away, so you really can't tell. It's the distinction is going to be very minor. So it's developing the tools and technology to get there, and that's why we would love to have as many scientists to join us in this quest to look and to develop these new standards as we measure gravitational waves and at a higher resolution that we previously had before. Because again, we were measuring 2 black holes before; those are massive. So the sensitivity to measure 2 black holes is nothing compared to the sensitivity that you would need to measure a Raman craft. So that's why this is going to be a bigger effort and more software is going to be required to really increase the resolution and decrease the noise in the data so you can actually be certain that you're looking at a Raman craft or a warp craft and not just a peculiar moving rock.
And outside of just like a Ramacraft or a warp craft, are there any other type of crafts that you're thinking, or those are the only two that you're really looking for using gravitational waves? Is there
Yes.
anything else?
No, we're limited to our own physics and imagination. We're trying to think of what else to look for, but we're unfortunately limited by our own feeble minds. Like that's all we can think of right now. I'm sure there's other things out there that advanced species can think of because it's like imagine 100 years ago asking somebody to predict the future just 100 years, they'd be so off. And it's like, well, what else could there be? I honestly have no idea. If we find something unusual, that's the one good thing about this technology, is it's just looking for massive objects moving around. So if anything is moving outside of its celestial, mathematics, it would pick up on it, and that would be alien, possibly something artificial, or more likely, again, something in the universe that we just don't fully understand yet, but still extremely valuable because now we discovered something new, and we never would have discovered that if we weren't looking for Rama. So again, it's like you have to motivate scientists to go through terabytes and terabytes of data. So Rama is a good carrot for the scientists ourselves, because again, these are long hours, and it's very hard for us. So we have to dream ourselves and motivate ourselves in our jobs, to really to get through all the data and work that this actually requires.
Thank you much, Gianni, for joining me on Rebelliously Curious, and we look forward to seeing what you're going to be doing next.
Yes, thank you so much. I really appreciate your time, and I've had fun.